Okay, let's jump right into the paper for today. It's called MemVerse, Multimodal Memory for Lifelong Learning Agents. So if you're working in this space, you know the biggest problem for any complex AI agent right now is memory. I mean, it's their Achilles heel.
Absolutely. They have this issue of catastrophic forgetting, and they just really struggle with any kind of long-term continuous task. Their internal state just doesn't scale.
And that is exactly what MemVerse is designed to fix. It's a model-agnostic sort of plug-and-play framework.
Right, built to create a reliable, scalable memory system. The goal here is genuine, lifelong, multimodal intelligence.
The real innovation, and this is the core of it, is this dual-path architecture. It's explicitly designed to mirror System 1 and System 2 thinking in humans, you know, fast and slow.
So you've got the slow pathway, which is the heavy lifting, the long-term memory, or LTM. It's a hierarchical, retrieval-based system organized into a multimodal knowledge graph.
And that handles all the continuous consolidation, the abstraction of raw experience.
Then you have the fast pathway. This is a lightweight parametric model that gets updated by distilling knowledge from the LTM.
Which gives the agent that rapid, intuitive recall. The knowledge gets baked right into its weights.
And the impact is, well, it's pretty dramatic. They hit state-of-the-art on ScienceQA, 85.48% with GPT-4 Mini.
And crucially, it speeds up memory access by about 89% compared to standard RH. So it has the performance and the speed. That's what we're going to dig into today, how they pulled it off.
And that combination of performance and speed comes from directly tackling the flaws in our current systems.
Right.
I mean, when you look at a standard LLM or VLM agent, they're basically stateless. They treat every single query independently.
It's like talking to someone who gets instant amnesia after every sentence you say.
Precisely. And the two main memory solutions we've been relying on are just, well, they're fundamentally broken for this idea of lifelong learning.
Okay, so what are they?
First, you've got parameter-embedded memory. This is where knowledge is just stored in the model's weight.
Super rigid.
It's rigid, it's bounded, and you can't expand it without retraining the whole thing, which is just prohibitively expensive. And it's still a victim of catastrophic forgetting. You learn a new fact, you might wipe out an old one.
And you can't even see what's happening. It's a black box.
Exactly. And then there's the second solution, which everyone uses, external static storage.
Retrieval augmented generation.
Yep. And these systems just log interactions linearly. It's like dumping text logs into a vector database.
Yeah.
As that grows, retrieval gets noisy, it gets slow, it gets expensive.
There's no abstraction, right? It's just handing you back a raw chunk of text.
No abstraction at all. They can't tell the agent, hey, these 10 things you just learned are all related to one single concept.
So MemVerse is really stepping in to fix three things at once. Decoupling memory from the parameters, providing a structured way to organize it, and supporting that deep multimodal reasoning.
And the whole system is managed by what they call the memory orchestrator.
The traffic.
Kind of, yeah. It's a rule-based logic system. And this is Kino added trainable parameters. It just governs all the storage and retrieval between the two pathways.
I love that detail. It's not another neural net to manage the other neural nets. It's just logic deciding, do I need the fast answer or do I need to go look up the detailed structured knowledge?
Exactly right. It decides when to cache, when to consolidate, and when to kick off that distillation process to update the fast, intuitive path.
Okay, let's zoom in on that slow pathway then, the heavy-duty knowledge engine. Before we even get to the structure, how does it handle all the different kinds of input? It's fully multimodal.
It is. And this is a really clever alignment step they do first.
What's that?
Before any input images, video, audio gets stored, it's first converted into a textual representation.
Ah, so they use something like GPT-4 Mini to caption an image or Whisper to transcribe audio?
Exactly. It's a normalization step. By converting everything to rich text first, they make sure that any relationship or entity they extract later can be consistently linked back to the original raw data. It keeps the memory grounded.
So that knowledge is created, but it doesn't go straight to permanent storage, right? It hits the short-term memory first.
Yes, the STM. And its job is purely about local consistency and efficiency. It's just a sliding window, holding the most recent K-queries, the immediate context.
So if the agent needs to remember something that just happened, it checks there first.
Which is massively efficient. It avoids a slow, redundant retrieval from the deep memory. And that consolidation into the long-term memory, the LTM, that only happens periodically.
When enough new persistent knowledge has built up.
Exactly. And that LTM, it's not just a big database, it's a paired structure. You have specialized knowledge graphs, and then you have the original raw text chunks they came from.
Okay, so why 3 specialized knowledge graphs? Why not just one giant one?
That's the critical question. A single massive graph would just become unwieldy. It would have the same problems as RA. So they segment it based on the type of knowledge, kind of like how human memory works.
Interesting. What are the types?
The first is core memory. This is for durable, user-specific facts, preferences. It's for personalization.
So if I tell the agent I hate cilantro, that goes into core memory.
Exactly. Then you have episodic memory.
Right.
This is time-ordered, event-based. It captures specific interactions. Last Tuesday, the user asked me about French poetry while showing me a picture of a cat.
So the core memory knows I like cats in general, but the episodic memory remembers that specific event.
Precisely. And finally, you have semantic memory. This is for abstract general knowledge. It knows the concept of a feline, but not my specific cat's name. It knows the relationship between poetry and literary history.
That's what gives it the edge over a RAG. It's highly targeted retrieval instead of just searching a giant list.
And this leads to the construction process. It's really sophisticated. They use a powerful LLM, like GPT-4o Mini, as a knowledge abstraction engine. It reads the raw input and compresses it into key entities and relations.
Which become the nodes and edges of the knowledge graph.
Right. But what's really genius is that every single abstracted node in that graph keeps a pointer back to the original source data.
The original text chunk, the image, the video. It's grounded.
So they get the efficiency of a knowledge graph, but they never lose the traceability. If the agent needs to know why it believes something, it can follow that pointer all the way back to the source.
So that's the slow, deliberate system 2 thinking. How do they build the fast path, the intuition?
This is where we shift gears. The parametric memory is internalized. It's stored as weights in a dedicated lightweight language model. In the paper, they used a Qwen 2.57b model as the backbone.
So instead of going out to the library, the LTM, every time, they're teaching a smaller student model to just recall the facts instantly.
That's a great way to put it. Its whole job is speed and generalization. It mimics the high-quality retrieval of the slow system, but it's fast, it's differentiable. It's how they cut down that computational overhead.
And they build it using periodic, supervised fine-tuning, knowledge distillation, basically. How does that training process work?
They construct these training data sets. Essentially, they create triplets for the small model. The answer retrieved from the reliable LTM, and then the target output.
So the powerful LTM is the teacher?
Yes. The small, fast model is optimized to generate the exact same answer the slow memory would have retrieved. It's constantly learning to match its teacher. This ensures the parametric memory evolves in sync with the external knowledge graph.
Okay, that sounds really effective for speed. But what about the trade-offs? Doesn't cramming all that knowledge into a smaller model mean you lose some fidelity?
Well, this is where the results really speak for themselves. The traditional RAG inference time averaged over 20 seconds a question.
20 seconds, okay.
Retrieving directly from their structured LTM knowledge graph, which is already faster, took about 8.26 seconds.
Still pretty slow for a real-time conversation.
Right, but the parametric memory retrieval time, just 2.28 seconds.
Wow, okay. That's a huge difference.
That's an 89% acceleration over RG. That's the metric that makes a lifelong learning agent actually feasible to deploy in the real world.
Let's look at the benchmarks then. Starting with general reasoning on ScienceQA, getting state-of-the-art with 85.48% is...
Yeah,
that's impressive. It shows the structure works across different domains.
It does, but what's even more compelling to me is how it handles dynamic, complex data, specifically video. If you look at the MSR-VTT data set for video text retrieval, the improvements are just colossal.
How big are we talking?
For text video retrieval, they jumped to 90.4% recall. The baseline, a strong model like CLIP, was stuck at 29.7%.
Wait, from under 30% to over 90%.
Exactly. And a similar leap for video to text. It really is a massive, non-trivial jump.
So why? Why does the MemVerse framework unlock such a huge gain specifically on video?
It goes all the way back to that initial knowledge construction phase. Instead of trying to do RAG on raw video frames, which is incredibly expensive, it uses the reasoning of GPT-4o Mini first.
To build the knowledge graph.
Right. That big model extracts and stores complex semantic relationships between frames, captions, and descriptions in the MMKG. So when the smaller model goes to retrieve something, it's retrieving rich semantic meaning. not just raw pixels or text.
That brings up a fascinating point from the paper, the dependency on the base model. They found that the effectiveness really varied depending on which foundation model they paired it with.
You did. When they tested it with the Quinn models, for example, the improvements were only modest. Even when MemVerse retrieved the perfect piece of knowledge, the Quinn models struggled to actually integrate it into their reasoning.
But with GPT-4 Mini, it showed a massive benefit.
A massive benefit. It had a much greater innate ability to synthesize that retrieved knowledge and apply it.
So what does that mean for designing agents going forward?
It means that a high-quality memory system is necessary, but it's not sufficient. You also need a strong foundation model with robust reasoning abilities to actually use the knowledge you retrieve.
The quality of the retrieval is only half the battle.
The ability of the agent to use it intelligently is the other half. The structure provides the knowledge, but the base model provides the wisdom on how to apply it.
Okay, so to sum up the contributions here, MemVerse gives us this cohesive, unified memory framework. It's really vital for agents to move towards true lifelong learning.
It successfully marries the speed of parametric recall, that intuition, with the depth and structure of the slow hierarchical retrieval memory, the deliberation.
And by structuring all that multimodal experience into the knowledge graph, it gets scalability and highly targeted retrieval without the noise and redundancy that just cripples simple vector stores.
The results really prove it. A robust, well-designed memory architecture is the vital missing piece for the next generation of AI agents.
Which leaves us with a final thought for you, our listener, to take away.
If the efficiency of that fast parametric memory depends on distilling knowledge using a small model, like Quinn 2.57b, to mimic the retrieval of the much slower, more powerful system, where is the ultimate ceiling on the agent's knowledge? Is it limited by the compression capacity of that smaller student model? Or is it constrained much earlier by the initial reasoning power of a larger model, like GPT-4o Mini, that built that rich semantic foundation in the knowledge graph to begin with? That balance between the quality of the foundation and the efficiency of the distillation, that's what's going to define how far these agents can really go.